So it's a real pleasure being here because I have a personal attachment to the program. One of my graduate students actually went through this program some years ago, Matt Fago. And I have to say we were both extremely impressed. So it's really a joyride. On the other hand, it's also very academically rigorous, so brace yourself for a bit of work as well. And today I'll be talking about a subject that really is a pervasive subject. So materials are everywhere. So if you're going to be involved in modeling and simulation of any type, chances are that as part of your PhD thesis, you'll have to contend with materials issues in one way or another. And multiscale modeling, as you'll see, is today basically the standard paradigm for availing ourselves of high fidelity material models. Okay, so most of the work that I'm going to present is part of the Caltech PSAP Center, the Predictive Science Academic Alliance program, which I direct. It's one of 5 centers funded by DOE and NSA over the center, over the country. And the main question that we ponder at the center is basically how far can we push our codes and our material models and still be predictive? Okay, so can we really predict material behavior and the behavior of complex systems under extreme conditions? So that's kind of our leitmotif, okay? And of course, you cannot ponder such a general question in a vacuum. So what we did from the start was to identify a challenging overarching application that would allow us actually to pursue, okay, the question in a concrete way. So we specifically chose hypervelocity impact. Okay, so you see here some examples of hypervelocity impact tests. And this is when you have a projectile that strikes a plate perhaps at 10 kilometers per second. So you see here what happens, that of course that's a very, very violent event. It really sets in motion very complex physics and very complex material behavior. So initially you can have, for instance, an impact flash where you have the formation of plasma. And in later stages, you can have the formation of debris, okay, and debris clouds. And these are things that you can actually measure in the lab. So in fact, one of the things that we chose this application is because we could carry out the tests in our own lab facilities. And then each one of these things that you can measure, the intensity of the flash or the fine structure of the debris cloud, then becomes a predictive challenge. Okay, so the question is, can you predict these things? Or go and predict these things if you can, okay? So here's an example of how we do these simulations. Okay, so these are particle simulations, okay, based on optimal transportation theory, where you have the projectile perforating the plate, and you can see, again, the formation of the debris cloud, forward cloud, backward cloud. And so we can generate many of the things that you can measure in the lab, and then we can compare and see how predictive we are. Okay, so this is some of the lab facilities that we have in-house. Again, this a typical simulation, okay, in this case of hypervelocity impact at 5 kilometers per second. And the question is how well we can actually predict reality. Okay, so if we look at the anatomy of one of these simulations, okay, you can see, of course, that a lot goes on. Okay, you have impact, you have complex material behavior, very high pressures, very high temperatures, very high strain rates. So the anatomy of a typical computational campaign is as follows. So you can think of it as consisting of several layers. Okay, so at the top layer, what we do is, of course, we don't do just one calculation, but we actually do thousands of calculations. Okay, what we call ensembles of calculations. And the objective is to garner statistics. So we want to, so the systems we are simulating are to some extent random. They can have random inputs, or they can become chaotic, for instance, fraction fragmentation. Okay, and then the question is how well can you pin down the behavior of the system and what is the level of uncertainty in your predictions. And for that, it's not enough just to send one calculation, but you have to do literally thousands of them, actually statistical sampling. And at this level, the purpose of the uncertainty quantification campaign, as it's called, is to, as I was saying, garner statistics and determine design margins and also levels of uncertainty. Okay, so that's very typical of the way we conduct calculations these days. It's not just doing one hero calculation, but actually literally doing thousands of them, okay, and quantifying uncertainties. At the next level, okay, so you peel off the QMU layer, and then so you're looking at doing individual calculations. So here's where you have to contend with the global geometry of the system you're simulating. Okay, so maybe a CAD model. You have to worry about boundary conditions, initial conditions, for instance, impact velocity of the impactor, the thickness of the plate. So these are all things that are passed into the solver, and the solvers are supposed to bundle all this information and move it forward in time. Okay, so this layer, the layer of the solvers, of course, is very sensitive to the details of the simulation, to the geometry, as I was saying, to the boundary conditions, to the initial conditions. However, okay, so if you move down one level, then at this point you're looking at individual material points, and these individual material points represent local material elements. So these are small bits of material that only see local conditions of deformation and temperature, and they're completely insulated from the geometry of the system. So at this point, once you come down to this level, to the level of an individual material point, you have lost sight of the particular geometry that you're simulating, you've lost sight of the particular boundary conditions, and you're looking specifically at material behavior, so the behavior of small samples of material, okay? And that behavior is is driven by local conditions and takes the form of material laws, okay, constitutive laws, what have you, okay? And if you keep looking down in length scales, then you find that, in fact, material points are not just blobs, but they have a lot of structure themselves, okay? So you start looking under the microscope, perhaps, and you see that an individual material point is not at all a point, but may have a polycrystalline structure, okay? So it really represents what is known as a representative volume. So then, if you keep looking down, maybe each one of the crystals, you begin to see individual defects, such as dislocations. You keep looking down, you start seeing individual atoms, and now you're at the level of quantum mechanics. So is this hierarchical point of view, okay, that is perhaps describes best the anatomy of a modern computational campaign, if you want. And what I would like to focus on today is the description of the material at this level. So no matter what you do, the flow of information of a typical calculation will always take you at some point at the level of individual material points. And there the question is, can you describe that behavior? Okay? So that sets the boundary conditions. And so, okay, this is a summary more or less of what I said. Okay, the material points, material models really sit at the core of full system simulation. So the flow will always take you to a material point, and you'll have at some point the need to describe the behavior of those material points, okay? And that behavior is purely physics or chemistry. So at this point, you're completely insulated from the details of the global geometry, boundary conditions, and so on. And you're just facing physics-based modeling. Then the other thing to be pointed out here is that, okay, because material models really are the core of the simulations, they're really predictive bottlenecks. So the overall simulation, no matter how good a job you do at spatial resolution, at temporal resolution, okay, so you can refine the resolution of your global system as much as you want. If your material description is no good, your global simulation will also be no good, okay? So your simulations are only as good as your material models and never better. So material models are really predictive bottlenecks. You really need to give them a lot of attention, make them really predictive if you want to have any chance at being globally predictive, okay? And so how do you come up with high fidelity material models? And I think the consensus at this point is that the behavior of materials, for instance, in a hypervelocity event is so complex. Okay, there's so much physics that is set in motion that it's really impossible to just model that complex behavior empirically. Okay, so there is no way that anybody, no matter how much intuition, can sit down at a table and throw an exponential here and a polynomial there and do a good job at describing all that complex behavior. You really have to look at the physics in detail. And the physics is multiscale. Okay, so really the only game in town in terms of developing high fidelity material models is multiscale modeling. Okay? So, okay, what is involved in multiscale modeling? So as I was saying, the reason that you need multiscale modeling is the physics of materials is really multiscale. So say, for instance, you're trying to characterize the strength of materials. Okay, so how do materials deform at high levels of stress and temperature and strain rate, for instance? Okay, so your global simulation may be at this level, so now you start looking down length scales and time scales. And so in a typical metal, you begin to see the polycrystalline structure. So you see that, in fact, these material points are not points at all, but themselves, have quite a bit of structure. Okay, so the first level you encounter at the SEM level, for instance, you begin to see the polycrystalline structure. Then if you look within individual grains, then you find that the behavior of each one of these grains is in fact far from being homogeneous. Okay, and you see that typically you develop very fine subgrain structures, okay, that I'll come back to in a second. Then if you keep looking down in the length scales and time scales, you begin to see individual defects, so dislocations, vacancies, and so on. Okay, so of course these are mediated very directly by the atomistic structure of the material, but still are at a continuum length scale. Okay, so maybe the scale of microns or hundreds of nanometers are still within the purview of continuum models. And then if you look at individual defects, then of course here you see the atomistic structure of matter, and you look at individual dislocations, you may see the core structure of each one of these dislocations, which, as you know, are line defects in crystals. You begin to see maybe kinks in the dislocation line, and you can start using atomistic models to compute basic properties, such as core energies or kink mobilities, okay, that give you the behavior of the material at this level. And there are also many material properties that can be computed at the quantum mechanical level, such as equation of state, maybe some transport properties, and that, as I was saying, you can calculate them from quantum mechanical calculations. And okay, so here you are. Here you have a typical hierarchical structure for, say, modeling strength in a metal. So what is the big deal? Why don't we just go ahead and do it? So of course, I mean, multiscale modeling is much more easily said than done. So the question is, how do you actually do it in practice in a way that you can actually do the models in actual calculations, okay, buy you some actual computational capability. The essential difficulty is that there are many vastly disparate scales. Okay, so you start at the atomistic level with quantum mechanics, and between that and your engineering application, okay, there could be maybe 10 orders of magnitude in length scales and also in temporal length scales. So quantum mechanics will never do. Okay, there's a lot that happens between quantum mechanics and your engineering applications that determine the microscopic behavior of materials, and somehow has to be modeled in some systematic way. Okay, so whereas there are some processes that happen at the atomistic level, they're rate limiting. So, okay, lattice defects, transport, and so on. As I was saying, the microscopic processes of interest, maybe ductile fracture or irradiation damage or aging of materials, may happen at length scales that are completely microscopic. And there's a big gap in between, huge gap. Okay. Also in terms of time scales, so if you're looking, for instance, doing a molecular dynamics calculation, there a typical length time scale will be maybe femtosecond. Okay, you may be interested in aging of materials. That happens over years. So again, a huge gap in time scales that somehow you have to fill in if you want to do aging, model aging in a multi-scale fashion. Also, the spatial scale gap, okay, so you have to go from angstroms to maybe millimeters and meters. And at this point, there is really no brute force computational scheme that will take you from A to Z, okay, just by brute force. Okay, so no matter how much computational power you throw at it, okay, so exascalars beware, okay, you'll never be able to go from quantum mechanics to aging of materials, for instance, in a completely just computational way, okay, by brute force. So you really have to do something clever along the way. And you have to use physics and math, algorithms, and do something clever along the way. Brute force will never take you there, okay? Which in a way is nice, okay? So if it were just a matter of building a bigger computer, then it would be kind of boring, okay? But as it turns out, okay, there is still room and a need for being clever, and the cleverness really comes in multiscale modeling and simulations. How do we actually do it? Okay, provided that we cannot just do it by brute force. Okay, so say that you're, okay, so now I'm going to give you fill in some details as to how you can actually bridge length scales in a practical way so that at the end of the day you have models of effective behavior that you can actually use in simulations. Okay, so say you're Galileo Galilei and you're pondering the cutting edge question of the time, which is how do you model beam bending. And okay, so most beams at the time were made of wood. And of course, okay, so it's clear that wood has a lot of microstructure, so it's composed of cells. And okay, but so the cells maybe could be in the millimeter scale or sub-millimeter scale, whereas a typical beam could be several meters in length or in span. So clearly you have a multi-scale problem here. So if you're Galileo Galilei, so what do? You say, well, okay, fine. This is a multi-scale problem, but there is strict separation of scales. So the length scale that I'm interested in is much, much larger than the length scale of the microstructure. Okay? So it turns out that under these conditions, if you have strict separation of scales, then you can do things, you can do clever things. Okay, and of course, very often you're interested in the engineering application, so you want to know just what is the macroscopic behavior of your system, and you don't really care so much what happens at the individual cell level. Okay, so you may have millions and millions of cells. You don't really care so much what happens in cell 500,002, okay? You really are interested in the microscopic behavior. Okay, so some way we would like to get rid of the microscale and come up with an effective model that we can use in simulations where somehow the microscale has already been eliminated and it's taken into account in some effective way, okay? However, you may still wish to have a return option, okay? So what does that mean? Okay, so very often you're not just interested in macroscopic averages, but you may be interested also in knowing what happens at the microscale, so also at the individual cell. For instance, suppose that you're interested in the failure of the beam. So we know that that would be mediated by processes that happen at individual cells, cell crushing, cell shearing, things like that. So in some conditions, you may wish this return option. So you want to have an effective theory that allows you to go back if you need to and query the conditions that happen at the microscale. Those may be important especially if you're interested not just on average behavior, but in the extremes of the fields, okay? Because maybe those are the ones that are important for failure processes or some other processes. And I'll show you an example later on where that's exactly the case, where this return option is really important, okay? So this is the objective. So we have an engineering system that has structure on multiple scales, but there is strict separation of scales. So somehow we want to eliminate the details and come up with a uniform model that has already eliminated the microscale, Okay, and that, so the defining property of this effective model must be that somehow it's indistinguishable from the original model at the macro scale. So when you test the uniform, so the effective model and the original model, under macroscopic conditions, they're indistinguishable, okay? So in this case, for instance, you may be Galileo Galilei may have been interested in computing what was the deflection of the beam when you hang a weight. So somehow your effective model must give you the exact deflection for any weight that you hang at the tip. And that's the defining property of your effective model. Okay, so you have to eliminate the microstructure, yes, okay. But the effective model has to be exact at the macro scale. So in effect, basically, the original model and the effective model have to be indistinguishable under macroscopic testing. And that's basically what defines your effective model, plus the condition that, as I was saying, in some cases you wish return clause to have a return clause. Now, in the case of the Galileo beam, okay, so the microstructure is already built into the material. Okay, so it's just the structure of the material. There are many cases where the microstructure happens as a result of deformation. So originally or initially, the material is uniform. So you deform it somehow, and in response to that deformation, the material develops microstructures. In this case, of course, it's a bit more difficult because you don't know to begin with what the microstructure is. You have to predict what the microstructure is, okay? And this is an example taken from the lab of Rick James. And what you see here is shape memory alloy that is tested under biaxial loading. And you see here under the microscope some of the beautiful microstructures that are developed by these materials, okay, as part of their behavior. And so in many cases, the microstructures are also very fine, so there's strict separation of scales, so you can play the game. And in this case, the objective would be to develop an effective model, okay, that you can use at the macro scale that somehow has eliminated, again, the microstructure, but that gives you a macroscopic response that is indistinguishable from the original system, okay? And these kind of situations perhaps are more generic in the sense that you don't know what the microstructure is beforehand. It's part of your prediction. Okay, so fine, but how do you do it? Okay, so of course there are many methods that have been developed, some of them going back to the 19th century. Okay, statistical mechanics was really intended to be a method, a multiscale method, where you go from thermal vibrations to microscopic, equations of state. So there are many methods for bridging length scales. Some of them are better than others. So let me give you an example just to convey the flavor. So there are some situations where the behavior of materials is governed by energy minimization. So basically, there is some energy functional, and the material will develop microstructure in such a way as to minimize its energy. So in this case, there is a standard theory called the calculus of variations that provides a recipe, basically a crank that you have to turn, that at the end of the day will give you the effective behavior of the material. And physically or intuitively, the scheme is very clear. Okay, you may have a microscopic application. Okay, so I've chosen one at random, say deep drawing here, okay, of a cup. And so what you're supposed to do, so at this level you want to have an effective description of the material. You don't want to contend with microstructure. What you have to do is you have to consider what are known as representative volumes, so small volumes of material. And within each one of these representative volumes, somehow you have to pre-evaluate all the possible microstructures that will occur. Okay, so typically in metals, you have microstructures of this type. This is an actual SEM picture of a deformed metal. You see that deformations at the micromechanical level are very non-uniform. Okay, so the metals form microstructure. And so the objective is somehow to pre-evaluate all these possible microstructures, somehow also determine the most efficient ones, and based on those optimal microstructures, as they're called, pre-compute the average behavior of the representative volume. And that average behavior is what gives you the effective model, and that's what you use then, say, for instance, to simulate deep drawing. Okay, so that's the basic scheme. So the question is, okay, so how do you do it? And the basic properties of this scheme is that it does provide an effective model in the sense that the macroscopic response and the microscopic response are indistinguishable. It's a lossless scheme, as it's called, in the sense that because you're pre-accounting or pre-evaluating all possible microstructures, in going from the microscale to the macroscale, there is no loss of information. You somehow have pre-computed and pre-evaluated the effect of all possible microstructures. So the upscaling is lossless. It happens with no loss of physics. And this kind of modeling, because you know what are the optimal microstructures, at the post-processing level, once you've done the microscopic calculations, you can always go back. You can always generate microstructures of interest and query them for extreme conditions, maybe of pressure, temperature, not just average conditions in the element of volume, but also the extremes of the distribution. So this kind of scheme is very nice because it has built in a return option. As I was saying, this return option is important when the extreme values of the solution and not just averages are of some concern. So because of failure, because you're interested in nucleation, initiation, or some other reason. Okay. So let me give you an example where this kind of scheme actually is essential in the sense that, as far as I know at least, there would be no way of doing these kind of simulations without multiscale modeling of this particular type. And so the particular application concerns detonation of high explosives. In particular, what one wishes to understand is initiation sensitivity. So what is initiation sensitive to? And so the standard picture there is that, okay, so this, again, this is a multiscale problem in the sense that these HE materials have a grain structure, and then molecular dynamic simulations and also direct observation shows that at the subgrain level, the material develops microstructure. So when you look at individual grains, you find that the deformation is far from uniform, but it can localize along very narrow shear bands. Those shear bands actually deform much more than the average deformation of the material. You develop very high pressures there, very high temperatures, so you have hot spots. And so initiation, of course, is all about developing hot spots. It's no longer just about average conditions in the grain, but the extremes of the distribution. So here's how we do these kind of calculations in a multiscale fashion. So this is the flow of information. And you can think of this as an information boomerang somehow, okay? Again, it's not just upscaling, but upscaling followed by downscaling. So you start from some basic material properties that perhaps you compute using atomistic simulation or even quantum mechanical simulations. So here for these materials, these are molecular crystals. There is rather little information about the behavior of these materials. Okay, for instance, the plasticity of these materials, the strength of these materials. So we filled in those gaps doing ab initio first principle calculations. When I say we, I really mean my colleague Bill Goddard and his group. And there are a number of basic properties that we computed this way, and we used to populate the single crystal plasticity model that operates at the single crystal level. So this is supposed to be a material point, representative material volume, okay, that in a macroscopic simulation would sit somewhere within the mesh. And these are the typical microstructures, the optimal microstructures that give you the effective behavior of the material, okay. These are called sequential laminates. You can show actually mathematically that it is precisely these microstructures, the one that give the softest possible response of the material. So these are the optimal microstructures. And we can generate them analytically in closed form, and we can get the effective behavior analytically in closed form. That's great news. Anytime you can avoid doing calculations, that's great, because having solutions analytically in closed form really saves you huge amounts of calculation. So then this effective behavior is what we use here at the macro scale. We do some simulations. I'll show you of actual tests that are done in engineering labs. So in this way, you can actually bridge all the scales from atomistic to engineering testing. And then, because we're interested in hotspots, what we do is we look at individual material points, we query the microstructure, we look at the extremes of the distribution, in terms of pressure, deformation, temperature, and then we pass that back to our quantum chemistry colleagues, and they use these histories as initial conditions for carrying out full chemistry simulations at individual hotspots, and determine whether at that particular hotspot, in effect, there was initiation or not. So that's the kind of thing you can do with multiscale modeling. And I would say that you can only do with multiscale modeling. There's absolutely no way you could do the entire simulation at the quantum mechanical level. So these are some of the material properties that we compute from quantum mechanics. So for instance, elastic moduli, temperature of melting, basic properties like that are accessible to quantum mechanics and can be passed up to higher levels. So we're saying there is very little that is known about these molecular crystals, so for instance, PTN. So what are the active slip systems? What are the yield stresses for the activation of plasticity? So those are, for the most part, unknown, either were computed from quantum mechanical simulations. And at that point, we are in a position where we have a baseline model at this level. We can unleash the microstructural calculations and then compute effective behavior and use it at this level. So then we can go back at the post-processing stage, generate microstructures of interest, and then pass boundary conditions to our colleagues. Typically, the microstructures that you find are microstructures where you have extreme concentration of deformation at some points. So these are the hot spots. It turns out that the time scales in the development of these hot spots are of a microsecond. So if you go to somebody like Bill Goddard and say, please do a quantum mechanical calculation over a time span of microseconds, he'll say it's absolutely impossible. So just to demonstrate the connection with chemistry, we used a very simple single-step reaction kinetics as a placeholder to full-scale quantum mechanical chemistry calculations. And so then we try to make contact with engineering testing. So very often these materials are tested in a plate impact configuration. So you have a plate of PTN, and you have a fire plate that sent against the specimen maybe at 1,000 meters per second. So that induces a shock that goes through the thickness of the plate, and in some cases induces detonation or initiation. In some cases, it does not. So of course, the predictive challenge here is to determine when you have initiation and when you don't. And so the way we do the simulations in this case, is we just take a core of material through the thickness, and we apply boundary conditions, periodic boundary conditions around the perimeter of the core, and then this would be the computational domain. So it turns out that these days we have enough computational power that you can resolve the polycrystalline structure of the material explicitly. So here's where you can use brute force. In the old days, there were people that spent entire careers trying to characterize the effective behavior of polycrystals. So these days, at least this is a case where we don't have to be clever. So we have enough computational power that we can actually resolve explicitly the polycrystalline structure, and we do. So this is a typical mesh that we would do in the calculations. So this is a typical simulation. So what you're showing here is the effective model being exercised. So what this effective model is giving you are average conditions. Not peaks, but average conditions. So you see some fluctuations here in velocity in this case, and those fluctuations are due to the polycrystalline structure. So there are some fluctuations, but definitely not hot spots. Something you could call hot spot and could be responsible for initiation. So again, so this is a map of temperature. So you see some fluctuations, but again, very mild fluctuations just due to the polycrystalline structure. And what I'm showing here is that, so I've taken two material points at random, and I'm showing the evolution of the microstructure, predicted by the microstructure model, at each one of those material points. Of course, there are thousands or perhaps millions of these material points, and this is just a sampler. And what you see is that at individual material points, you develop very fine microstructures, okay, where there are regions that are very highly deformed, okay, that attain very high temperatures, and conditions that are, in fact, highly in excess of the macroscopic averages. So whereas the macroscopic average doesn't really give you any useful information regarding hotspots, of course, the microstructural model gives you at least some handle or some information about, again, extreme values in the distribution of pressure, deformation, and temperature. And then you have collect some hot spot statistics, which is what I'm showing here. So, well, this is the evolution of a typical hotspot, how the temperature rises. This is the molar fraction of a reacted product, okay, showing, in this case, full initiation. And, okay, because we have a microscopic model with thousands of material points, thousands of microstructures, we can collect statistics regarding hotspots. So, for instance, you can plot here the number of hotspots where the reacted molar fraction exceeds a certain value. And, okay, so as we're saying, you have some handle on the statistics of these hotspots. And the payoff at the end of the day, why this is interesting, is because now, okay, you're not just confined to quantum mechanics, but you actually can make contact with engineering testing. The vast majority of tests that are done for these materials are done at the engineering level. Okay, so drop weight towers, things that definitely happen at the macro scale. Okay, and to make contact with these test data, and that's ultimately what you want to do to assess predictiveness. You have to make contact with test data. To make contact with engineering test data, you really have to go all the way to the macro scale. And so these some typical results from tests that would be conducted, for instance, at the Army Research Lab. And typically what they do is they plot in a logarithmic scale. This is what is known as a plot, the impact pressure versus the distance to detonation. And they find that there is this power law relation. Okay, so with the macroscale model, because we have control on hot spots, we can produce more or less the same plot and exhibit also power scaling of some type. So from the model that we use, we get an exponent, okay, which is 2.9, whereas for PTN, you get exponents in the lab that are perhaps 2.5. So there's still a little bit of a gap. You can see that the model, okay, perhaps is not exactly predictive, okay, but at least you're in a position where you can assess the predictiveness of the model, okay? So this is basically the best that we can do at this point. So, okay, so we know that if that's not good enough, then you can go back and refine the model. But at least we have a way to make contact with testing and assess predictiveness. So, okay, this is just a summary of this kind of methodology. Okay, so in a way, you can think of this as an optimal way of doing upscaling where there is no loss of information, and therefore you can always go back, okay? And the application to HE, okay, and specifically taking the simulation all the way to the engineering level, I think could only really be done this way. Now, just to give a counterpoint to this, okay, so not to give you the impression that somehow these relaxation methods are the panacea and that solve all multiscale models, let me give you a counterexample of a case where, okay, that is not amenable to relaxation. Okay, so the kind of upscaling that I described earlier. So it's also a multiscale situation. Okay, it has to do with fracture and fragmentation. And here, the multiscale hierarchy that you find is that the fracture, the ductile fracture of the material, is ultimately the net effect of the formation of voids and the coalescence of voids. So if you look at it as again, as a multiscale problem, so here at the top level, you have the formation of a ductile crack, okay, that causes the failure of the material. So if you start looking down, you see, okay, so individual voids that grow under the action, for instance, of hydrostatic pressure. Then, okay, these voids somehow nucleate at some point at the nanoscale by emission of dislocation. So that would be the nucleation event. Okay, so perhaps the nucleation sites are second phase particles, for instance, in steels or something that is pre-existing, or under extreme conditions, the nucleation sites can be maybe generated by vacancy aggregation. Okay, and then so at some point, you need to understand, therefore, the properties of vacancies. Vacancies are individual missing atoms or atomic level defects, okay, in metals. And so you need to know, you have to have control on the properties of individual vacancies, die vacancies, vacancy mobility, and so on, so you can evaluate the behavior of the material at this level. And this is something you can do at the quantum mechanical level. Okay, so specifically, this step where you go from distributed damage to localized damage is something that is not amenable to the kind of upscaling that I described earlier, because that upscaling, okay, is, okay, so this is what I said, okay, so avoid nucleation growth and coalescence. And fracture provides an example of a multiscale situation, again, where because the damage becomes localized to a plane, okay, it's no longer just a representative volume kind of situation. It's not about volumetric averaging, but somehow you, to get at the fracture properties of the material, you have to allow for localization of damage to individual fracture planes, okay, what are known as void sheets. So here the relaxation scheme would completely break down, would give you something that would be completely useless. Okay, here we're not in the market for constitutive models or equations of state. What we want is really fracture properties, which is a completely different type of physics. There are other methods that you can use. Of course, that would be another lecture. These are called optimal scaling methods. Okay, so those give you optimal bounds of the fracture energy, for instance, as a function of fundamental properties of the material, such as surface energy, hardening properties, and so on. Okay, so there are methods that you can use that actually give you the effective fracture properties you want at the end of the day. Okay, but it's, as I was saying, a counterpoint to relaxation methods. And the point is that there is not a panacea. There is not a single method that will give you all effective behaviors of interest. You really have different types of behaviors that require different methodologies. Okay, so just to give you an example of the kind of predictive capability that we can get in the area of fracture. So this is a very nice set of tests that were run at Lawrence Livermore by Jeff Campbell and co-workers. So what they did, they took a spherical shell, okay, made of steel, and they blew it up. Okay, so they had some, so they detonated some high energy material here on one side of the shell, and of course the detonation causes the shell to break up and undergo fragmentation, in fact, fine fragmentation. And the nice thing is that, okay, they showed okay, a lot of pictures of how the process takes place, and they also collected fragments. Okay, so they were able to recover fragments and provide statistics of, for instance, fragment sizes. So again, you have a data set that you can compare against to establish predictiveness or to assess predictiveness. So here you have some simulations that we do at the center of this particular type of test. Okay, so these are supposed to replicate the Campbell et al. Test. Okay, so you have, again, spherical shell, and so in this case, we just apply a simple drive that models somehow the detonation. You can see here the formation of very fine fragments. We do this with a material point method, so the way we model fracture and fragmentation is specifically by failing material points. And what the multiscale model tells you is exactly when you have to fail a material point. And you can see that in the, however, away from the center of the shell, then you have fragments that are much larger in size. Okay, so you have now measurements you can compare against. So this is the experiment, the velocity at some point in the shell versus time. This is what you get from the simulation. So it's not entirely perfect, but then considering that we didn't simulate the drive exactly, okay, so we are, I think, in the ballpark. And okay, so these are the fragments recovered from the simulation. Okay, so at the end of the simulation, we went around, we looked for the fragments that are in excess of a certain size. We put them back together, so we collected so these are the recovered fragments, not from the experiment, but actually from the simulation. And so now we can put together histograms of fragment size, and I can compare with the ones that were measured experimentally. Okay, so here you have the experiment. So this is the size of the fragments. So this is the number of recovered fragments. Okay, And here you have the fragment size from the calculations and the number of recovered fragments. And you actually see more or less a reasonable correlation, regarding the, for instance, the mean size of the large fragments. There are 2 peaks in the distribution, both in the experiment and in the simulations. I really have no idea why there are 2 peaks, okay, and why we actually get 2 peaks. As maybe it's just a complete fluke, but okay, so you count your blessings. And generally, okay, in this way, again, perhaps the key point is that we can make contact. So with engineering testing, macroscopic test data, in this case, from the experiment of Campbell et al. Okay? So this is just a summary of the main points. So at some point when you do simulation of materials, you have to contend with material behavior somehow. Okay, I'm sure as part of your PhD thesis, whether you come from physics or from chemistry, from computational mechanics, computational physics, mathematics, at some point you'll have to contend with some type of material behavior. And you'll find that more often than not, materials actually are multiscale. They exhibit structure on the multiscale, either built in from manufacturing or because of the deformation process itself. And material models are a critical predictive bottleneck. If you want to be predictive, you have to do a good job at modeling and simulating material behavior. Okay, so there is a need for high fidelity material models. Brute force won't do, so only game in town, multiscale modeling. So thank you for your attention.